Hi there, you're welcome back to another section of my YouTube channel tutorials. So in this video, I'm going to take you through how to determine the determinant of a matrix using the naive Gaussian elimination. In our previous videos, I showed you how to use the naive Gaussian elimination to simplify a system of equations, to find the solutions to systems of equations. If this is the first time you're visiting this channel, kindly subscribe so that you visit the older videos to get a better understanding of this concept. So let's get straight to what you have here. I have a theorem here for you to know before we get to what you come to do. Because our goal here is to determine the determinant of a matrix using naive Gaussian elimination. So the theorem is saying that let the matrix A be an n by n matrix, N by n means that a square matrix, it has the same dimension. So it can be 2 by 2, it can be 3 by 3, 4 by 4. It should be a square matrix. Then if matrix B, which is also n by n matrix, results from adding or subtracting a multiple of one row to another row, then the determinant of A is the same as the determinant of what B. Yep. So whenever you perform row operations simply by multiplying one row by a constant and subtracting or adding to another row, then the resulting matrix you get should have the same determinant as the original matrix. So that's the concept behind that. Then the next theorem, but not the theorem, that you should know that whenever you have a triangular matrix, so assuming you have a triangular matrix and you're having something like A, B, C, then you have 0, 0 here, then D, E, you have 0, F, So at this point, if you want to find the determinant of any triangular matrix, you simply have to multiply the element on the principal diagonal. That's all. That is all. So have that also in mind. So whenever we get an hypertriangular matrix, to find its determinant, just multiply the elements on the principal diagonal. And for what I have here, I'll simply get A times D times F. That's all. That gives me my determinant. So with these two in mind, we can go straight finding the determinants using the naive Gaussian elimination. The reason why I show you this is that naive converts a matrix into an hypertriangular matrix, right? So let's take an example here. So find the determinant of the matrix below. So the matrix is matrix A, giving us 25, 5, 1, 64, 8, 1, 144, 12, 1. So for this matrix, to find the determinant of this matrix using the Gaussian elimination method, we need to simplify this to an hypertriangular matrix, right? So you know that the steps involving naive Gaussian elimination is 1, forward elimination, then 2, backward substitution. But take note, we involve backward substitution to determine the values of the unknowns. In this case, we are not having any unknowns. We are only interested in converting this to an hypertriangular matrix. So we would therefore take the backward substitution out. It's not involved. So the only thing to do is the forward elimination. So let's see how we do that. So for the forward elimination, the key thing here is what we call multiplier. So multiplier is being multiplied by a pivot row, then it's subtracted or added to a second row in order to eliminate a particular entry in order for us to get our upper triangular matrix. So let's see. With our matrix, I have 25, 5, 1, 64, 8, 1, 144, 12, 1. This is row 1. Here is row 2. This is row 3. So always for the first set of elimination, we use row 1 as our pivot element. As our pivot row. So we will multiply the multiplier by that, then either subtract or add to the others in order to eliminate this. So if I want to eliminate 64, I need to multiply a certain thing by row 1 so that it will become 64. Then I can subtract it from row 2 to take this 64 out. So the multiply is simply giving us this entry which I want to remove divided by my row 1 entry. So I'm going to have my multiplier m is equal to 64 over 25 by row 1. So you realize that when you multiply 64 over 25 by row 1, this 25 will cancel and I'll get the first entry to be 64. And I can straight away write my row operation as row 2 minus 64 over 25 row 1, and it maps to row 2. Whatever we get, we replace row 2 with that set of entries. Okay, so now we can go ahead and what is 65 on 24? So for 65 on 64 on 25, we are getting 2.56. So my row operation simply is row 2 minus 2.56 R1 all maps to row 2. So for the first part, I'm going to get something like 25, 5, 1. Then here, my row 2 is where I start to apply the row operation. So row 2, 64. I'm going to get 64 minus 2.56 times 25 all maps to row 2. What is 2.56 times 25? And that gives me 64. So 64 minus 64, here will be 0. Okay, I'll have 8 minus 2.56 times 5. Okay, so 8 minus 2.56 times 5. And that should give me negative 4.8 here. Negative 4.8. Then finally, I have 1 here minus 2.56 times also 1. So it's the same as 1 minus 2.56, obviously negative 1.56, right? So the next set is for me to take the 144 out. So let me write this simply and move to the next. So at this point, I've taken this and gradually we are moving. So I want to take this 144 out. As usual, our row 1 is our pivot row. So I'll take a multiplier, and the multiplier in this case will be 144 over 25, as I said earlier. So 144 over 25 times row 1 becomes my new multiplier. Then my row operation is row 3 minus 144 over 25 multiplying row 1, all going into row 3. So what is 144 over 25? So 144 over 25 is 5.76. So the row operation becomes row 3 minus 5.76 R1 moving into row 3. So at this point, I'm going to do my calculation. 25, 5, 1. Row 1 is untouched. Row 2, 0, negative 4.8, negative 1.56. Then my row 3 becomes what? 144 minus 5.76 multiplying 25. And that should give us 144 minus 5.76 multiplying 25. That is 0. Okay, so please take your calculator as we walk along so that you get the understanding very, very well. So I have 12 here. So 12 minus 5.76 times what? 5. That's the second entry. So 12 minus 5.76 times 5. And that is giving me 16, negative 16.8. Negative 16.8. Then finally 1 minus 5.76 times 1. That is negative 4.76, obviously. So at this point, I've been able to take all these out. I'm only left to remove this. Whenever you are doing row operations or converting a matrix to upper triangular matrix and you reach this level, we focus on the inner 2 by 2 matrix here. Okay, so at this point, this becomes my new pivot row. So R2 and R3, right? So I simply have a multiplier negative 16.8 over what? Negative 4.8, right? Yes, multiplying my row 2 as my multiplier. So what is this? Negative 16.8 over negative 4.8, and that is 3.5. So my multiplier is 3.5 R2. Okay, so the row operation is R3 minus 3.5 R2, all going into R3. So I rewrite my matrix 25, 5, 1. Row 1 is always on tag because that is where we're looking at to. Then here negative 4.8, negative 1.56. Okay, here becomes 0. Then here is what we have to solve. So this is it. This is a row operation. So row 3, which is negative 16.8 minus 0.5 multiplying 25. We punch this on a calculator. Negative 16.8 minus 3.5 times 25. And that should give me 0, right? So that should give me 0, right? So the next thing to do is you have, sorry, I multiply by 25. It shouldn't be 25. Take note. Actually, we are multiplying it by our pivot. Our new pivot is root 2. So sorry for that. You multiply this negative 0.5 by negative 4.8 instead. Okay, negative 4.8 instead. So on that, you get negative 16.8 minus 3.5 multiplying negative 4.8, and that is 0. So this side becomes negative 4.76 minus 3.5 times what? This one, not 1, because this is now a new pivot row. So negative 1.56. So you simply do this. Negative 4.76 becomes plus 0.5 times 1.56, right? And that is giving us 0.7, simply 0.7. So at this point, we are done with our forward elimination. So our final matrix is giving us 25, 5, 1, 0, 0, negative 4.8, 0, negative 1.56, 0.7. So from the beginning, I told you that when we get an hypertriangular matrix, the way to find our determinant is simply by multiplying all the elements on the principal diagonal. So our determinant is simply equal to 25 times negative 4.8 times 0.7. And you point this on your calculator. 25 times negative 4.8 times 0.7. And that is giving us negative 84. But the matrix given wasn't this matrix. The matrix given from the question was A, which was in this form. But we have performed row operations simply by multiplying one particular row and subtracting it from the others. And that satisfies our theorem here that if the B was formed as a result of adding or subtracting a multiple of one row to another, then the determinant of A is equal to determinant of B, right? So we can boldly say that our determinant for the matrix A is equal to negative 84, which is the determinant of this matrix, because this matrix is a derivative of the original matrix A, but just that we have added, and you get it, that row operation something. Thank you for being with me in this video. Don't forget to like and share. See you in the subsequent videos too.